I'm going to illustrate this technique with an example which I've taken from the book by Torres del Castillo, Differentiable Manifolds, a book which I've referred to earlier as a standard textbook which I follow in my differential geometry videos, at least for most of it. This particular metric that I've chosen is a slightly non-trivial one. It's given by this. Faces would be more familiar with this in the following form. ds square is g mu nu dx mu dx nu, or which in this case is dr square by 1 minus kr square plus r square d theta square plus r square sine square theta d phi square. This is a metric with a very specific significance, but I'm not going to go into that right now. Maybe by the time we end the calculation, you will be able to see what the significance is. Now, one of the first things that you need to do is create the connection 1 forms. But for that, you need the gamma ijk coefficients. The gamma ijk derive, at least for a Riemannian geometric case that we are talking about here, using this particular equation and evaluating each one of the gamma kij's in turn. However, that is really rather difficult. So I'm going to use another technique which is going to enhance the efficiency of the calculation a lot, and one which is perhaps very familiar to most people who have done a GR course, which is the following. We will just define a Lagrangian given by half gij x dot I x dot j, and it follows that the Euler-Lagrange equations of motion which follows from this particular Lagrangian happens to be the same as the geodesic equations for this particular manifold. And the geodesic equations happen to be the following. Where t is some parameter, doesn't have to be the time. This is the geodesic equation, and if you can find out the geodesic equation by starting with this Lagrangian and calculating its Euler-Lagrange equations of motion, you can immediately read off the gamma mu nu lambdas from there. I'm actually lapsing into a physics habit of using Greek indices often, and sometimes using Latin indices. But here it is a purely spatial calculation, no special relativity or minus plus 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 metric implied here. It's of course a purely plus 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 metric, as you can see. And so we will just stick to ijk's mostly, except when habit sort of forces me to use an equation like this. But you should be able to gather that I mean x double dot I plus gamma ijk x dot j x dot k equals 0. That's the geodesic equation in this particular situation. So for our calculation, this of course is something which doesn't really involve advanced differential geometry techniques, the kind of things that I'm really talking about here. But these are also important techniques, and let me just illustrate how this goes also. Although frankly, if you already know how to do this, please feel free to move ahead. Skip to the next section. So in our particular example, what we have is a Lagrangian L given by r dot square by 1 minus kr square plus r square theta dot square plus r square sine square theta phi dot square. All this with an extra half. The half is simply to make some of the 2's that come out of the calculation go away. In fact, you can immediately see the effect of the half right now. If you want to find out the R equation for this, you have to calculate del L del R dot, and that will immediately give you R dot by 1 minus kr square. You have got rid of the 2. And you also need the del L del R, which is also pretty easy to calculate. You have one obvious term from this, which is 2r theta dot square, but there's a half, so that 2 goes away. Similarly, you have an r sine square theta phi dot square. The slightly trickier thing is to calculate this, which will have an r dot square, and you will also have a 1 minus kr square whole square with a minus sign, and minus 2kr square coming from here. Once you take care of that half in front and the two minuses cancel, this is what you're going to get. So now, the Euler-Lagrange equation for this particular thing is going to be d dt of del L del R dot equals del L del R. And when you differentiate this with respect to t, what you're going to get is r double dot by 1 minus kr square, that's one term, plus another term which comes from differentiating this, and that's going to be something we have already seen just a while ago. This time there's no half to cancel out the thing, so you get 2kr up there, and an extra r dot, so you get r dot square. And that's equal to kr square by 1 minus kr square whole square, r dot square, plus r theta dot square, plus r sine square theta, phi dot square. And finally, if you want to write this exactly in this fashion, what you need to do is rewrite everything, bring everything to one side, multiply out by 1 minus kr square, and so the equation which you finally get, r double dot, is kr by 1 minus kr square. One of these factors would cancel, of course, minus r into 1 minus kr square, theta dot square, minus r to 1 minus kr square sine square theta, phi dot square, equals 0. So this is a geodesic equation obeyed by the coordinate r. And from this, you can immediately write down that this is the coefficient gamma 1, 1, 1. This one is gamma 1, 2, 2. And this one is gamma 1, 3, 3. And for gamma with an upper 1, there are no other non-zero connection coefficients or Christoffel symbols, as we would say in the case of Riemannian geometry. Okay, so that was the R equation. What about the theta equation? Let me just copy out the L, because I will need to take a look at this when I work out the theta equation once again. So let's just copy this onto the top of the next page. And now, for the theta equation, what we need is del L del theta dot, which is of course pretty simple. It's going to be r square theta dot. And you also need del L del theta, which is what you get from this term. And you get twice r square sine theta cosine theta phi dot square. So the derivative of this being equal to del L del theta gives you r square theta double dot plus twice r dot theta dot equals twice r square sine theta cos theta phi dot square. Sorry, there's no 2 here. The 2 cancels out with the half. I forgot about the half. So there's no 2 here. And so now, the geodesic equation for theta component comes out with theta double dot plus 2 by r dot theta dot minus sine theta cosine theta phi dot square equals 0. And all these gamma symbols with 2 at the upper index can be figured out directly by looking at this. We are going to get to that soon, but let me just first figure out the geodesic equation for phi. So del L del phi dot is r square sine square theta phi dot, and phi is what we would call a cyclic coordinate in mechanics. There is no phi in this expression, so del L del phi is simply 0. So the time derivative of this, well, I'm calling it time simply because we are used to calling it time in Lagrangian. This is just any parameter which parameterizes the geodesic. So r square sine square theta phi double dot plus twice r sine square theta r dot phi dot plus twice r square sine theta cosine theta theta dot times phi dot. That's equal to 0. So when we cast this to the standard geodesic form, what we get is phi double dot plus 2 by r sine square theta. Sorry, not the sine square theta, that also cancels. R dot phi dot plus, okay, let's be careful about that here, 2 cotangent theta, theta dot phi dot equals 0. So now that we have the three geodesics, all three, the R1, let me just copy this to the next page so that we have all of them together. We can take a look at them. What we have are these three. This is the R1. We already have the phi 1 sitting here. Let's put the theta 1 just next to it. Just write it here. So we have our three equations. So now, this one of course is equation number 1, this is 2, this is 3. At least we are labeling our coordinates x1, x2, x3 with r, theta and phi in that order. And now we can immediately read off the non-zero gammas. So gamma, let's start with this one. Gamma 1, 1, 1 is kr by 1 minus kr square. Gamma 1, 2, 2 is minus r into 1 minus kr square. Gamma 1, 3, 3 is minus r 1 minus kr square times sine square theta. So we are just reading off these numbers. What about the 2, 1? So here you have to be a bit careful. This is going to give you gamma 2, 1, 2. But notice that you have both gamma 2, 1, 2 and gamma 2, 2, 1 here. And it's the sum of the two really. And since these gammas, at least for Riemannian manifolds, are symmetric in the low index, what we get is gamma 1, 1, 2 is gamma 1, 2, 1 equals 1 by r. And sorry, not gamma 1, these are all gamma 2's up here, of course. These are for the second equation. And then gamma 2, 3, 3 is minus sine theta cosine theta. Finally, well, that would be the phi equation. From here, what we are going to get is gamma 3. Now I'm regretting writing the phi equation first. Anyway, gamma 3, 1, 3 and gamma 3, 3, 1 are both equal to 1 by r and gamma 3, 2, 3 and gamma 3, 3, 2 of course. 2, 3 and gamma 3, 3, 2 are both equal to cotangent theta. Let me warn you about one thing. This symmetry in the lower two indices is a property of the Christoffel symbols in a Riemannian manifold if you are using the coordinate basis, not in other bases. So be careful about that. Right now, of course, the symmetry is there. So now that we have all the gammas lined up, now comes the time of using our advanced differential geometry trick. This Lagrangian technique that we have used just now is actually quite standard, and many elementary general relativity textbooks also show you how to do that. But most will not talk about the kind of trick that I'm going to talk about now, because that requires, as I said, some advanced differential geometry background to begin with. So our actual content of what I'm trying to show you today begins at this point. Now that we have the gammas, let's write down all the non-zero connection 1 forms. Remember, we have this formula for the connection 1 forms, the definition really, which is you start with the connection coefficients and multiply them by the basis form like this. Of course, this is the sum over all k. So now that we have all the gammas lined up here, let's write down the condition 1 forms. Gamma 1, 1. That's simply going to be gamma 1, 1, 1, theta 1. And theta 1, of course, is dr. So we have kr dr by 1 minus kr square. But there is no other gamma with the first two indices, the top one and the one to the left here, being 1. There's no gamma 1, 1, 2 or terms like that. So this is all that you have in gamma 1, 1. What about gamma 1, 2? There also, you will have only one term. This is the only term that will contribute, and you will get minus r into 1 minus kr square d theta. D theta because that's theta 2. And gamma 1, 3, 3. Just get rid of the definition, or let's move the definition out here. And let's make some space to the right. I don't want to go to the next page right now. Gamma 1, 3 is gamma 1, 3, 3 theta 3. So it's minus r into 1 minus kr square sine square theta d phi. Well, let's continue. Gamma 2, 1. Well, there's only one gamma symbol, condition coefficient, with 2, 1 in this position. That's gamma 2, 1, 2. So that's 1 by r d theta. Gamma 2, 2. Well, that will come from this term. 1 by r dr. Because that's gamma 2, 2, 1 theta 1. So that's dr here. And gamma 2, 3. Well, that will come from this. Minus sine theta cosine theta. Theta 3. That's d phi. Finally, what about the gamma with 3 up here? 3, 1. That will come from gamma 3, 1, 3. So 1 by r d phi. Gamma 3, 2. From this, cotangent theta d phi. Gamma 3, 3. That will show you something which you have not seen in all the other gammas that we have calculated so far. You actually have two terms contributing here. One from gamma 3, 3, 1 and the other from gamma 3, 3, 2. So you get 1 by r dr, that's gamma 3, 3, 1 theta 1 plus gamma 3, 3, 2 theta 2. That's cotangent theta d theta. So these are our non-zero gammas. In this case, all the 9 gammas that are possible. Remember, there are n square connection 1 forms. In this case, n is 3. All of the 9 are non-zero, and we are going to use these expressions to calculate our Riemann curvature tensor.